Two concepts haunt modern science like unsolved riddles.
Information, the currency of the digital age, the stuff of genes and neurons, perhaps the fabric of reality itself.
And consciousness, the inner light of experience, the fact that there's something it's like to be you reading these words. For decades, these mysteries have been treated as separate problems, but that's beginning to change.
The connection becomes clearer once we ask what information actually is, and recognize that it comes in two distinct but intimately connected forms.
The first definition, information is order, measured as the distance from the statistical distribution representative of thermodynamic equilibrium. This is information in something. The ordered state is a low entropy state, and entropy measures the system's proximity to the most probable equilibrium state. Therefore, a system is far from equilibrium if its components are statistically correlated, because correlation among components is order. When parts are correlated rather than independent, you have structure. The system occupies a state that's improbable relative to chance. You can predict something about one part by knowing about another. The opposite, maximum entropy, is defined by complete statistical independence among components. This is the molecular chaos assumption underlying Boltzmann's H-theorem at equilibrium. Each particle's state is statistically independent of every other's. No pattern, no structure, no organization, just randomness. So information in something is internal statistical correlation, the degree to which a system's components hang together rather than behave independently. We have a formal measure for this integrated information FPHI, developed by the neuroscientist Giulio Tononi and colleagues. FUS quantifies how much a system is more than the sum of its parts, the information generated by the whole that can't be reduced to its parts. A system with high FEF has deeply integrated components. Knowing about one part tells you about other parts. FA measures the information in something, the internal order, the departure from molecular chaos. The second definition, information as predictive data, information as knowledge. This is information about something. Here, the information encoded in a system has utility, a functional role in keeping the system far from equilibrium. The internal configuration is in some way isomorphic to relevant structure in the environment. It's a model. This is also about statistical correlation, but a different kind. Not correlation among a system's internal components, but correlation between the system and something external, correlation with the environment. For example, a dolphin's form is correlated with hydrodynamics, and an eagle's wing is correlated with aerodynamics. The internal configuration mirrors relevant environmental structure. This correlation is information the system uses to maintain its ordered state. We have a formal measure for this two-semantic information developed by SFI's David Wolpert and Artemy Kolchinsky, and later by theoretical physicist Carlo Rovelli. Semantic information is the mutual information between a system and its environment that is causally necessary for the system's continued existence. That means if you remove a gene that represents knowledge, you will get a dysfunctional organism that can't maintain its far from equilibrium state. Semantic information measures the information about something external correlation that serves survival. These two kinds of information are genuinely distinct. You could, in principle, have a highly integrated system, high F, that isn't correlated with anything external, just an arbitrary pattern of internal dependencies. And you could have a system with environmental correlation but low integration, parts that track the environment independently without communicating with each other. But here's the key insight in any stable system that persists over time. These two are causally coupled. Internal order, high F, requires anticipating and counteracting perturbations from the environment. To maintain the information in, you need information about. A system with high FEF but no semantic information is possible but unstable. The systems that persist, that maintain high FEF over time in noisy environments, are precisely those whose internal integration serves predictive purposes. The integration isn't arbitrary, it's about something. The internal correlations encode external regularities. Sustainable FA requires semantic information.
In adaptive living systems, they co-evolve, and we call this process learning. From learning to consciousness. When a system learns, whether through evolution, development, or experience, it isn't just becoming more internally organized.
It's becoming better aligned with the world it inhabits. Internal order grows because the system is discovering, compressing, and exploiting patterns in its environment. The structure inside the system mirrors the structure outside it. This insight sits at the heart of modern theories of learning and perception, including Karl Friston's free energy principle, which shows that any system that persists over time must reduce surprise by building internal models that anticipate what comes next. Learning from this perspective is the process by which internal structure becomes increasingly tuned to the world. So far, nothing here requires consciousness. Even simple organisms and some non-living system as well can build rudimentary models that help them persist. But at some point in evolution, something qualitatively new happens. Every adaptive system models its environment. But in more complex systems, the model begins to include the system itself as part of what's being modeled. The map comes to contain the mapmaker. This recursive turn is subtle but profound. When a system can represent itself as an agent acting in the world,